Okay, so in this video, big M is equal to 1.8 kg, little m is 0.4 kg. First L, or length of the cord, is 3m meters. L rod was 5 meters. Any velocity I used was in meters per second. Omega, rad per second. Alpha, rad per second squared. Mu k was 0.16. F, any force I used was in newtons. Acceleration was in meters per second squared. D, or displacement, was in meters. And yeah, those are the units and some of the values I used in this video. Hello, Mr. Long. So in part A, we can begin by setting up the conservation of energy. So MEI is equal to MEF. MEI breaks down to initial potential energy, and MEF breaks down to KE final at the point 25 degrees below the initial release point. So KEF plus PEF, and PEI breaks down to MGHI. The right side breaks down to 1/2 MVF squared plus MGHF. Now we can cancel out the M's, which leaves us with GHI is equal to 1/2 VF squared, which we are looking for, plus GHF. And we can move over, now we can isolate for VF, so we can move over the final PE by subtracting on both sides. So GHI minus GHF is equal to 1/2 VF squared. We can multiply by 2 on both sides. So 2 times GHI minus GHF is equal to VF squared. Now we can square root both sides. So square root of 2 times GHI minus GHF is equal to VF. Now our HI is simply 3 meters because it's given to us as the length of the cord. And we can see in the diagram right here. So we could plug that in. Minus GHF. And our HF is going to be the potential energy at this point, the new point. So to find the final height, we subtract the height as fallen from its initial height. So we can do that by setting up our trig. So the length or hypotenuse is 3 meters. So 3 sine 25 will give us our height right here, because sine is equal to opposite over hypotenuse. So if we want to find the opposite, we multiply the hypotenuse on both sides, which gives us 3 sine 25. So now we subtract this height from our total height right here, and then that will give us the potential energy final at that point. So we plug that in. 3 minus 3 sine 25, all under square root, is equal to VF. Now we could go and plug this into our calculator. So square root of 2 times 9.8 times 3 minus 9.8 times 3 minus 3 sine 25 is equal to 4.985 meters per second. So that's our final speed at that point. And since we're looking for the speed, we don't need direction. So that's our answer for part A. Okay, so for part B, we could set up our Pythagorean theorem, solving for A net. So A net squared is equal to AC squared plus A tan squared. And we know that AC is equal to V squared over R. And we know that A tan, if we look at our diagram, we could draw our FG vector. And we could draw our X axis and our Y axis. So I'm going to label this as FGY and this as FGX. And to find A tan, we use the adjacent side of FGX to find A tan. So we know that since this angle is 25 degrees, this angle is 25 degrees. So we set up our net force in the X direction. Net force X is equal to MA tan. Net force in the X direction is composed of FGX. So FGX is equal to MA tan. FGX breaks down to FG cosine theta equal to MA tan. And since FGX is the adjacent side, that's why we use cosine. And I'm going to just go ahead and plug in 25 degrees. And FG breaks down to MG, so I'm going to just break that down as well. So MG cosine 25 is equal to MA tan. We could go ahead and cancel out the M's. So we're left with A tan is equal to G cosine 25. So we go ahead and plug this all in to our Pythagorean theorem. So A net squared is equal to B squared over R parentheses squared plus G cosine 25 parentheses squared. All right, and we found the V in the previous problem, which is 4.985, and our R is just 3 meters because it's given to us as the length of the cord, and G is just 9.8. So we go ahead and plug that all in. So A net squared is equal to 4.985 squared over 3. This is all squared. And I'll keep G as G. So G cosine 25 squared. Now we go ahead and plug it into our calculator. So 4.985 squared over 3 squared plus 9.8 cosine 25 squared gives us a total of 147.5. So A net squared is equal to 147.502. Now we square root both sides. And A net is equal to 12.145. So A net is equal to 12.145 meters per second squared. And since we're looking for the magnitude, we don't need a direction. Okay, now so for part C, we're asked to find the angular acceleration, magnitude of the angular acceleration. So we just set up the formula A is equal to R angular acceleration. And we just isolate for angular acceleration. So angular acceleration is equal to A over R. We simply divide it by R on both sides. So now our A that we're going to use is A tan. So we go ahead and go back to our equation right here. A tan is equal to G cosine 25. And we just find that on our calculator. So 9.8 cosine 25 is equal to 8.881. So we go ahead and plug that in. 8.881 over R, which is just 3 meters. And we can plug that into our calculator as well, which gives us a total of 2.961. So A, angular acceleration, equals 2.961 rad per second squared. That's our answer for part C. Again, looking for the magnitude. So we do not need a direction. Okay, so for part D, to find the tension in the cord at the lowest point, we look at the diagram. At the lowest point, it's right here, and it has an FG vector pointing down, and it has a T vector pointing up. So the T vector also serves as part of our FC, centripetal force. So we can set up FC is equal to mv squared over r, which is equal to mac. And in this case, FC is also equal to T minus mg. So we could isolate for T, which is what we're looking for. So we just add mg to both sides of FC. So T is equal to FC plus mg. Now we just plug in mv squared over r for FC. So T is equal to mv squared over r plus mg. And we know what r is already, which is it's 3 because it's given to us in the problem. And the only thing we don't know is v at the lowest point. So we go ahead and look for v at the lowest point by setting up conservation of energy. So PEI is equal to KEF. And now PEI breaks down to MGHI. KEF equals to 1/2 MVF squared. VF is what we're looking for because it's the speed at the lowest point. And we can set up PEI equals KEF because at the lowest point, all the energy that's stored as potential energy is now converted to kinetic energy. So we cross out the M's. G, HI is just 3 because it's the length of the cord. So G times 3 is equal to 1/2 VF squared. Multiply 2 to both sides. So we get 2 times 3 times G is equal to VF squared. We can radicalize both sides, square root both sides. And we get rad 6 times G is equal to VF. So we could just plug that into our calculator. 6 times 9.8, which gives us a V of 7.668. So V at the lowest point is 7.668 meters per second. And we only need the magnitude, so we don't need the direction. So we go ahead and plug that in to our formula over here. So T is equal to M 7.668 squared over 3 plus mg. And I'm just go ahead and plug in 1.8 for m because that's the mass that's given to us in the problem for the steel ball. Okay, so now we know that T, tension, is equal to 1.8 times 7.668 squared over 3 plus 1.8 times G. So we go ahead and plug that all into our calculator. 1.8 times 7.668 squared over 3 plus 1.8 times 9.8 is equal to 52.919. So magnitude of T is equal to 52.919 newtons. And that's our answer for part D. Okay, so for part E, we could set up conservation of momentum. And the initial momentum breaks down to big M V1I plus little m V2I equal to m, big M, V1F plus little m, V2F. F stands for final. Okay, so little m, V2I cancels out because it's at rest. So we can just rewrite this as big M, V1I is equal to big M, V1 final plus little m, V2 final. And then we could plug in our numbers. So big M is 1.8 for the steel ball. V1, I, like we solved in our previous parts, is just equal to 7.668 meters per second. So we go ahead and plug that in as well. 7.668 and equal to 1.8 V1F plus M, little m, V2F. And little m is really just 0.4 because it's given to us in the diagram and problem. So I'm just plug that in, 0.4. Now, using our calculator, we just solve for the left side. So 1.8 times 7.668 is equal to 13.8. So left side is equal to 13.8. And on the right side, we're left with 1.8 times V1 final plus 0.4 V2 final. And now we could just isolate for V2F. So we could subtract 1.8 V1F from both sides. So 13.8 minus 1.8 V1F is equal to 0.4 V2F. Then just divide 0.4 from both sides. So we're left with V2F is equal to 13.8 minus 1.8 V1F over 0.4. Now, since the problem states that the collision is perfectly elastic, we know that KE is conserved, so we can set up KEI is equal to KEF. So that breaks down to 1/2 big M V1I squared plus 1/2 little m for the block V2I squared equal to 1/2 big M V1F squared plus 1/2 little m V2F squared. And since the block is initially at rest, we just cross out that on the left side. And we can also cancel out the 1/2s. And now we can plug in the numbers just to make things a little bit easier. So big M is just 1.8. V1I is just 7.668. And that's going to be equal to 1.8 V1F squared plus 0.4 V2F squared. Okay. Now we use our calculator to solve for the left side. So 1.8 times 7.668 squared is equal to 105.836. So we can go ahead and write that. 105.837 actually. And then it's still going to be equal to 1.8 V1F squared plus 0.4 V2F squared. But we could just plug in the V2F that we found over here. So it's going to be plus 0.4 13.8 minus 1.8 V1F over 0.4. And it's all going to be squared. So now we foiled this on top. So it's going to be 13.8 minus 1.8 V1F times 13.8 minus 1.8 V1F. 13.8 times 13.8. Use our calculator. It's going to be 190.44. So 190.44. Then minus 13.8 times negative. But we don't need a negative right now, so it's just going to be 1.8. So it's going to be minus 24.84. Now we do the same thing for this. V1F. Okay, and then now it's going to be negative 1.8 times 13.8. So that's going to be minus, and then same thing, 24.84 V1F. Now it's going to be 1.8 times 1.8, which is 3.24. So it's going to be plus 3.24 V1F squared. Now we can combine these like terms. So it's going to be 190.44 minus 24 times 2, 49.68 V1F plus 3.24 V1F squared. Okay. So this is going to be the top that we foiled. So we're going to go ahead and plug this all back into that. So let me see. So it's going to be 105.837 is equal to 1.8 V1F squared plus 0.4 190.44 minus 49.68 V1F plus 3.24 V1F squared. Okay. And then at the bottom was 0.4, so we still have to square that. So on the bottom it's just going to be 0.16. Okay. Parentheses. Now we just simplify this parentheses by putting everything on top over the 0.16. So we just do 190.44 divided by 0.16. And we do the same thing for each number. Okay. So now we have 105.837 is equal to 1.8 V1F squared plus 0.4 1190.25 minus 310.5 plus 20.25. Hold on. Let me erase this to get some more room. I'm gonna go ahead and bring this on here. Rewrite it on here. 1190.25 minus 49 minus 310. My bad. 310.5 V1F plus 20.25 V1F squared. Okay. So this is all going to be multiplied by the 0.4. Now we distribute the 0.4, so it's going to be 105.837 equals 1.8 v1f squared. Then distribute the 0.4. So we're left with 1.8 v1f squared plus 476.1 minus 124.2 v1f plus 8.1 v1f squared. Now I'm going to go ahead and subtract 105.837 from both sides so that we could set it equal to 0 and then quadratic formula and all that. So I'm going to subtract 105.837 from both sides. So we get 0 on the left side is equal to, I'm going to go rearrange this just so that's in the form of quadratic formula. So it's going to be 8.1 v1f squared minus 124.2 v1f and then we combine the like terms. So this is actually going to be 8.1 plus 1.8. So it's 9.9. 9.9 v1f squared minus 124 v1f. And then it's going to be 476.1 minus 105.837, which gives us 370. So it's going to be plus 370.263. So now we go ahead and just plug this all in to our quadratic formula, which the quadratic formula is just v1f equals 2 negative b plus or minus rad b squared minus 4ac over 2a. And then our A is going to be 9.9. Our B is going to be negative 124.2. And our C is going to be 370.263. So now we just plug this all into our quadratic formula. Negative 124.2 plus minus rad negative 124.2 minus 9.9 370.263. Okay, over 2 times 9.9. So then if we use our quadratic formula, on our calculator, we get 7.668 and 4.877. And now we know that 7.668 can't be right because that's the speed at the lowest point before. So our speed after is going to be 4.877. So V1F is going to be equal to 4.877 meters per second, positive. And that's our answer for part E. Okay, so for part F, to find the time it takes for the block to come to a stop, we can set up VF equal to VI plus AT. VF is going to be 0 because it comes to a stop. And VI, in this case, is now going to be the velocity after the collision, the velocity of the block after the collision. So we can actually use this equation from part E because it's a different perspective now. So we go ahead and plug in the speed we found in part E for V1F. So we can just do that on our calculator. 13.8 minus 1.8, 4.877 over 0.4. That gives a velocity of 12.554. So we just plug it in. 12.554 plus AT. And now to find AT, we can just set up our net force on the block M, little m. So net force is equal to little ma. And the only force acting on the little block, on the block, little m, is F of k. So F of k is equal to ma. F of k is just mu k mg equal to ma. The m's cancel out. So we're left with A is equal to mu k g. Mu k is given in the problem as 0.16. So A is equal to 0.16 times 9.8, which is just 1.568. And it's going to be negative since it's against the motion of the block. So 1.568 meters per second squared. So we go ahead and plug this in to our formula right here. So it's going to be 0 is equal to 12.554 minus 1.568 t. Okay. Now we subtract 12.554 from both sides. And we get negative 12.554 is equal to negative 1.568 t. And now we just divide negative 1.568 from both sides. And we get t is equal to 8.006 seconds. So that's our answer for part F. Okay, so for part G, since it's a new scenario, I'm going to set up this little table. This is the first scenario, this is the second scenario. And then I'm going to set up common form, so VF squared minus VI squared equals 2A delta X. So I'm going to find the original distance that the block travels. So VF is just going to be 0 minus the speed that we found in the previous parts, which is 12.554 squared equal 2 negative 1.568 that we found in the previous parts as well, delta X. Now we just use our calculator. To find 12.554 squared, which is 157. So it's going to be negative 157.6. And then 2 times 1.568. 3.136. So we're going to divide that. So negative divided by negative 3.136 equals delta X. So now we can just do this on our calculator. And that gives us a delta X of 50.256. So the original delta X is equal to 50.256. And now for the new scenario, I'm going to set up the same thing and find the new VF. And then the new displacement is going to be 3/4 of the original distance. So it's going to look like this. And we can go ahead and just plug this all into our calculator to find the VF. So it's going to be 2 times negative 1.568 times 3/4 times 50.256 plus 12.554 squared. So this is plus. There we go. Which gives us 39.4. So VF squared is equal to 39.4. We can square root that on both sides to get VF equals 6.28 meters per second. So that's our new final velocity. So we go ahead and set up conservation of angular momentum. So Li equals Lf. And on the left side, it's going to be CPR. On the right side, it's going to be I total times omega. I total because the block strikes and it strikes the rod and sticks to it. So we're going to need both of their eyes. So I total breaks up to I rod plus I block times omega. So on the left side, it's just going to be MVR. And we go ahead and plug in the numbers. So M is just going to be 0.4. The V is going to be the V that we just found, so 6.28. And then the R is going to be 2/3 L. So it's going to be 2/3 of 5. So on the right side, I rod breaks up into 1/3, big M for the mass of the rod, R squared. R for this R is going to be R rod squared plus little m for the block, R squared times omega. So I'm going to simplify the left side. It's going to be 0.4 times 6.28 times 10/3. It's going to give us 8.37. So the left side is equal to 8.37. And then I'm going to go ahead and plug in the rest of the values. So it's going to be on the right side. So it's going to be 1/3. Big M is just 1.1. The R of the rod is 5. So it's going to be 5 squared plus little m, 4.4. And then the R for the little m is going to be 2/3 of 5 because it's given right here. And it's the same thing for the left side. So this is going to be squared all times butt cheek. So now we can simplify the parentheses. So it's going to be 1/3 times 1.1 times 25 plus 0.4 times 10/3 squared, which gives us 13.611. So 8.37 equals 13.611 butt cheek or omega. So we could divide 13.61 from both sides. And we get omega is equal to 0.6151. So that's our answer. omega is equal to 0.6151 rad per second. And we don't need direction since it's magnitude. Okay, so for part H, to find how high the rod block system will rise at the collision, we can set up change in PE equal to change in KE, and the change in PE is equal to the M total because now we're adding the big M plus little m. H is what we're going to look for, equal to 1/2 I total omega squared. Okay, so now M total is going to be big M plus little m, which is just 1.1 plus 0.4. GH equal to 1/2 I total, which in part part G, I found to be 13.611. So I'm just go ahead and plug that in again. So 13.611 omega squared, and then omega we found in part G, which was 0.6151 is squared. So now we just plug this all into our calculator and isolate for H. So let me just isolate for H real quick. So H is going to be equal to 1/2 13.611 times 0.6151 squared over G times 1.1 plus 0.4. Okay, now we just plug this into our calculator. It's going to be 0.5 over times 13.611 times 0.6151 squared over 9.8 times 1.5, which gives us an answer of 0.175. So H will equal 0.175 meters. And that's our answer for part H. Okay, so in part I, we're asked how the angular speed would change if the rod was lowered and the block strikes at L/2. So we could just set up linear momentum again. So we do Li equals Lf, and then Li is going to be CPR. Lf is going to be I total times omega. CPR is going to be the same as in part G, except now that R, instead of 2/3 times L, it's going to be 1/2 times L, because that's what is a new scenario. So it's going to be 0.4. Well, it's going to be MVR equal to I total, which is just I rod plus I block again, times omega. So now M is just 0.4 still. V is still 6.28. Now the R is going to be 1/2 times 5 equal to 1/3 big M R rod squared plus little m R squared omega. This we can plug into our calculator just to simplify it down a little bit. So 0.4 times 6.28 times 5/2. It's going to be 6.28. So 6.28 is equal to 1/3 big M R rod squared plus M R squared omega times omega. All right, so then now we just plug in the values for big M, R rod, and regular R. So 6.28 is equal to 1/3 1.15 squared plus 0.4 times 5 over 2, which is basically 1/2 times 5 squared times omega. Now we just plug that in and simplify it into our calculator. So it's going to be 1/3, 1.1 times 25 plus 0.4 times 25 over 4. Oops. Okay. Which gives us 11.67. So it's going to be 6.28 is equal to 11.67 omega. Now we divide both sides by 11.67. And we get omega is equal to, let me delete this, is equal to 6.28 divided by 11.67, which gives us an omega of 0.538. So omega is equal to 0.538 rad per second. And this is the magnitude, so no direction. And that shows that if we were to lower the rod to so that the block strikes it at L/2, it would decrease the angular speed. All right, so for part J, to find the period of the rod block system, we can use T of a physical pendulum, which is equal to 2 pi rad I, in this case total, over M total G D. And D is going to be measured from pivot to center mass, which means that we're going to have to find the center mass. So center mass is equal to big M times L/2 plus little m times R. Now, it's L/2 and R, which is 2/3 times L, because the reference point is from the pivot. So that's why it's L/2 and R equal to 2/3 L. So the bottom's going to be big M plus little m. Now I'm going to plug everything in. So big M is going to be 1.1. L is just 5, so it's going to be 5/2 plus 0.4 times 2/3 times 5 over big M, which is 1.1 plus 0.4, which gives us, if we plug it into our calculator, (1.1) times 5/2 plus 0.4 times 10/3 over 1.5, which gives us 2.72. So our center mass is 2.72, which is also RD. So we can go ahead and plug this into our T formula. And I total we found in the previous parts as 13.611. So we go ahead and plug that in as well. So T is equal to 2 pi times radical 13.611 over 1.5, because it's big M plus little m, G D. D being equal to 2.72. So we could plug that into our calculator. 2 pi radical 13.611 over 1.5, 9.8, oops, 2.72. That gives us an answer of 3.666. Whoa. So our period is going to be equal to 3.665 seconds. There we go. This is an S for seconds. So that's going to be our period and the answer for part J. Thank you.